So Professor Srikant was a faculty member in computer science and engineering in the computer science and automation department in ISC. Um, he retired just last year, and he had been a faculty since 1986. So he was the dean of faculty of engineering at ISC, and before that he had been the chairperson in the department of computer science and automation from 2001 to 2005. He did his PhD at CSA ISC, and after that he had joined as a faculty member. Professor Shikant's areas of expertise include compiling techniques, program analysis, and parallel programming languages. In these areas, he has authored a large number of papers in leading journals and conferences. He has graduated 20 PhD students and 27 master students by research, and about 100 MTech project students. So there is a lot to say about him. He's an awesome person, and even just sitting and talking to him is real fun. So I would really encourage all of you guys to be very interactive and ask him a lot of questions. So it's a great opportunity to learn a lot from him. So, sir, it's all over to you.
Thank you, Subhajit, for a very warm introduction. So let us get started without too much ado. So this lecture will be about optimizations in the compiler domain, local and global optimizations. So the outline of my lecture, there will be 3 lectures today, right now one, in the afternoon another, and tomorrow morning one more. So there is no need to rush through all the topics. If some things get left out today, right now we will cover it in the afternoon, etc. The outline of the lecture is here. So an introduction saying what is code optimization, etc. Then look at the basic types of optimizations, basic blocks, control flow graphs, some examples of local optimizations, and then directed acyclic graphs, value numbering, examples of global optimizations. This is the agenda for today's lecture. So we call it as machine independent code optimization. Well, so we must say what exactly it is and why it is needed. For example, if you consider the intermediate code generation process, it involves, so many operations, and in the process of generating the intermediate code, there are a large number of extra copies, a large number of variables whose extra copies are introduced. And then we simply assign, programmers in general, assign variables a is equal to 4, and then use a instead of 4, right? And then there are repeated evaluation of expressions. Well, this is more for convenience that happen. And such inefficiencies obviously can be removed by the compiler, and this process is actually called as code optimization. But optimization per se is a misnomer. We must actually call it as code improvement, but the name code optimization has stuck. The reason why code optimization is a misnomer is that when you run through an optimization pass for a particular program, which you can write very easily, no improvement may be possible. So in such cases, there is no optimization, per se. It is just that improvement is not possible in this case. So now, optimization or improvement may be in the time domain, or the memory domain, or the power domain. So in other words, when we are when the compiler compiles a program and performs these code improvements or optimizations, it may be given the agenda of improving the execution time, or improving the memory footprint of the program, or reduce the power consumption of the program. Each of these will become, very important on particular types of devices. And what are the side effects in some sense of the code optimization process? Most important, it changes the structure of programs, sometimes beyond recognition. For example, when we have a function call, there may be an inlining of the function. In other words, the function body replaces the function call. And if there is a loop, then the iterations of the loop may be unrolled. And then there may be some programmer defined variables which will be completely removed from the program for various reasons. So these are some of the changes that actually change the landscape of the program itself, and you may not even be able to recognize this after it is compiled. But that is okay, because the correctness of the programs is still valid. Basically, code optimization is a bunch of heuristics, and the percentage of improvement depends on program. Sometimes the percentage is 0. So you cannot guarantee that there will be a 10% or 20% improvement by the code optimization process. Okay. So there may be, there may not be, it depends on the program. And eventually, there are two basic types of optimizations. One is called as the local optimization, and the other set is called as the global optimization. So what are local optimizations? Well, these are carried out within what are known as basic blocks. We are going to look at basic blocks in some detail, but to bring, explain it here, it is just a straight line sequence of instructions with an entry at the top and possibly an entry or two at the bottom. So in between, in this sequence of instructions, there are no exits possible. Okay. So that is what is a basic block. So in such a basic block, whatever optimization or code improvement is carried out is called as a local optimization. So we will explain each of these as we go with examples. So right now it is going to be just a list of such optimizations. So local common subexpression elimination, then dead code elimination. What is dead code? Instructions that compute a value that is never used. Okay. And then reordering computations using algebraic laws such as commutativity, associativity, etc. And then a set of optimizations which are known as peephole optimization. So we will look at examples of each of these. So to do all this, we must introduce the minimum machinery, that is required. So let us do that. So what exactly is a basic block? I already gave you a very simple explanation. So basic blocks are sequences of intermediate code with a single entry and a single exit. So that is a basic block. And we will consider what are known as quadruple versions of intermediate code in our examples, just to make the explanations easier, because they are very simple. Quadruples are very simple to understand. Control flow graphs are the graphs which show flow of control among the basic blocks. We will see examples of this very soon. And then basic blocks are generally represented as what are known as directed acyclic graphs, which in turn will get represented as using the value numbering method. Okay, so I have actually thrown lots of words here. We will explain each of these in the coming slides. So an example of a basic block. Okay, so here is a high level language code, simple code, prod equal to 0. Then there is a for loop for I equal to 1, I less than or equal to 20, I plus plus. Prod equal to prod plus AI star BI. Very simple code, right? Now, when this code is actually converted to or compiled to intermediate code, this is what we get. So there are lots of temporaries T1, T2, T3, T4, T5, T6, T7, T8, right? So each of these compute a small quantity, and the rest of it adds up to the total, right? And then there is a branch instruction corresponding to the implementation of the for loop itself. So this is how the code would look like. Now, when we pictorially show the code, we have a small basic block consisting of just the two quadruples prod equal to 0 and I equal to 1. So this much. Then there is another basic block B2 with a large part of the most of the code in the program itself. And this basic block ends with a go to statement. But there are no other exits within the basic block itself. You should observe that, right? And this base, the exit at the end of this basic block goes back to the beginning of the basic block, or it exits to the basic block B3, which contains a stop statement. So the takeaway from this diagram would be the entire program consisting of several quadruples has been divided into 3 basic blocks, and each one of the basic blocks is a single entry, single exit sequence of code, and then with a go to possibly at the end of the basic block itself. And then the control flow among these basic blocks is shown by the arcs visually, but of course it is shown by go to in the program. So this is how the control flow graph and the basic block would look like. If there are questions, I will take them before we proceed further. Okay. So let me give you a more elaborate example, which will be used to demonstrate some of the optimizations as well. This is the bubble sort program, which almost everybody would know. So here is a for loop which depicts the number of passes, and then here is the internal for loop inside the I loop, in which we are going to examine pairs of numbers and then swap them, right? And here is the comparison, and here is the swap. It's a very simple bubble sort with no extra bells and whistles. So for example, there is no special jump out if array is already sorted, which can be detected, of course, but we are not doing all that because the number of quadruples will increase quite a bit. So a hand compiled version of this program into quadruples is shown here. And as you can see, even for this small program, it's a fairly large number of basic blocks, and the control, is a spaghetti code and so on. Yes, that's how it would be. So there are many, so every basic block either ends with a go to statement, or it just goes to the next one. Here, for example, in this basic block, there is no jump at the end of the basic block, but this has a jump, this has a jump, and this has a jump, okay, and this also has a jump. So please observe that this is how the control flow would be, okay, in the basic block. So there is not much to explain except to say that there are a large number of temporary variables which have been introduced by the intermediate code generator. That is number one. Number two, there are a number of possibilities for code improvement here. For example, I will give you just one example. The quantity 4 star j has been computed in many places. This is one place. Here is another place that it has been computed. Okay. And we will see that indirectly there will be many other places again. So each of these computations, which may sometimes be redundant. So we have to remove these redundant computations using a process known as the local code optimization, and in a bigger sense, a global code optimization process. That will be what we would be studying. and that all these optimizations will be carried out on the control flow graph, and that's the reason I'm showing you a couple of examples to drive home the point. Okay. So let us take a basic block like this. Now we are now dive a little deeper into local optimizations. What is the reason, for introducing what is known as value numbering, which I mentioned, to perform some of the local optimizations? So to give motivation, we can start by showing the basic block structure in the form of a directed acyclic block. So A equal to 10 is the first quadruple here, and that is shown as just a simple node, a constant 10, and that node is labeled with the variable's name, which is A. Then corresponding to B equal to 4 star A, right? So there is a node star with a label B with the left child as 4 and the right child as A. This is how the basic block is represented inside the directed acyclic graph. So now quickly I star j is here. So I star j, I and then the star j with a T1 here. Then we have C equal to T1 plus B. So that part is here, this is the C. Okay, there are two C's. Please remember that the second C overwrites the first value. So this is the old C or the first C. So you can see that it is showing T1 plus B. So T1 is the left child and B is the right child. Then we have T2 equal to 15 star A. So that is also here. That's easy to see. Then we have D equal to T2 star C. So that part is here, right? Then we have E equal to I. Well, I is already an old value, so there is no need to actually create a fresh node for it. We will simply attach E to the node I itself. Then we have T3 equal to E star J. Please observe that E is nothing but I and J already exists, and therefore T1, which was computed as I plus J, also qualifies to be called as E plus J, E star J. So T3, which is the E star J, will now be attached as a label to this node, which is nothing but I star J. So this is a striking example of what is known as a common subexpression elimination. I star J existed, E existed in the form of I. If we are able to find out all this information, then we can attach the label T3 to the star node and we have detected a common subexpression. And now then we can eliminate it also. So we don't have to compute T3 equal to E star J all over again. Then we have T4 equal to I star A. So that part, is here, right? Finally, C equal to T3 plus T4. So C is being reassigned a new value, and that is this. So the old value of C, is not relevant anymore. It is the new value which is relevant to us. So this is the directed acyclic graph representation pictorially for this particular basic block. So any questions so far? Okay. So, but let me go back a little bit. If you actually build the directed acyclic graph and represent it as a data structure, so using say some adjacency list or whatever, then our intention of performing common subexpression elimination, etc., becomes an extremely expensive process. The reason is, just take this particular node. We want to find out whether I already, E already exists in the directed acyclic graph. Then we want to find out whether E star j already exists in the directed acyclic graph. And if so, attach T3 to it. Doing this in this pointer representation, involves searching the entire directed acyclic graph, which is a very, very expensive process. So we require an easy way of representing the directed acyclic graph, which enables simple searching processes. Okay. So a simple way to represent directed acyclic graphs for this application is via what is known as value numbering, which is nothing but actually a variant of the hash technique, the hash table technique that all of us know already. So while searching directed acyclic graphs represented using pointers, it's a very, very inefficient process, whereas value numbering, which uses hash tables, is a very efficient process. That is the reason we represent directed acyclic graphs using hash tables. So what is the basic idea, central idea? The central idea is to assign numbers, which are called as value numbers, to expressions. Okay. So every expression in the basic block will be given a value number. So in what way? In such a way that two expressions receive the same value number if the compiler can prove that they are equal for all possible program inputs. So in other words, if I consider I star j, which has been computed early, and then I and j have not changed, so I star j is computed once again, then the compiler can immediately say that yes, I star j value is the same as before. Okay. So if you are able to come to such a conclusion within the compiler, then the two I star j's can be given the same value number. We will see how it gets done. So again, we assume quadruples with binary or unary operators. We use three tables. I am not going to get into too many details of how the whole thing is built, but because my pictures show you these tables, I must mention them. We call it as the hash table, the value number table, and the name table. I will give you examples of this. And what is the use of value numbering? They can be used to eliminate common subexpressions. I will show you how that gets done. They can be used to do constant folding. I will show you that also. And they can be used to do constant propagation. That will also be very clear in the example. Of course, it can take advantage of operators, commutativity, addition of 0, multiplication by 1, etc., etc. All this can be done very easy. Okay. So expressions are hashed, and that value that is stored in the hash table. Okay. So this is called as the value number of the expression. Then programmer defined names and temporary names are hashed, and they are all stored in the value number table. Again, names are also given value numbers because they exist. Finally, the names which are all equivalent are stored in the name list, and if they are constant, then there is a constant value which is stored along with it. Whether they are constant or not will be indicated by the constant flag. So these are the three simple data structures which will be used by the value numbering scheme. Okay. So let me explain with an example how the whole thing happens. So here is the high level language program with large expressions. And after it is broken down into quadruples, this is the version. So let me point out that there is a T1 equal to I star j, and then there is E equal to I, and finally there is T3 equal to E star j. So I star j happens to be a common sub-expression. Please note that. We will see how to detect it. Then we have A equal to 10 here. Then we have B equal to 4 star A. So A is a constant at this point. So 4 star A becomes 40. So this is an example of not only constant propagation, A, the value of A flows or propagates to this quadruple, and evaluating 4 star A is constant folding. Okay. So let's see how it gets done. A equal to 10, the name A actually is entered into the value number value this thing the table, which is the valnum table. Okay. And the value of 10 is recorded in the other table. Okay. Now, when we have B equal to 4 star A at this point, we search for A in the name table. We already get it, and we see that it is a constant, which is also shown by this particular, name table entry. We know that 4 star A can be computed as 40 at this point. So we make B get the value 40, and B is entered into the hash table. Now T1 equal to I star j, that is entered into the hash table, and T1 gets a value number. Then comes C equal to T1 plus B. So T1 is searched in the hash table. Well, it is present, no problem. Its value number can be extracted. Then B can be searched in the name table, and that has a value 40. So the quadruple T1 plus B now becomes T1 plus 40 after constant propagation. Then we have T2 equal to 15 star A. So A has a constant value. So the quadruple now becomes T2 equal to 150 and is accordingly entered into the value number hash tables. Now T2 star C becomes 150 star C. See, constant propagation can happen. T2 is a constant. So 150 star C is the new quadruple which is obtained. Now you have E equal to I. So this is again present, and E and I get the same value number. E star J, E is searched. It's the same value number as I. J is already present, and E star J becomes I star J, which is already available. So you actually get the same T3 equal to I star J. Okay. So which is a quadruple which is already computed. Now, that is why we have mentioned that instructions 5 and 8 can now be eliminated, because these are, corresponding to the computations which are redundant. Now, these two are simple. T4 equal to I star 10 is obtained by replacing A by 10, and C equal to T3 plus T4 becomes C equal to T1 plus T4. The basic idea is to use as few number of temporaries as possible in the final program. The final program will not have this instruction, and it will not have this instruction. It will have only the rest of them. Okay. So this is how the value numbering scheme enables us to perform constant propagation, constant folding, and more importantly, a common subexpression elimination as well. Okay. Any questions so far? So you can look at these tables and get a better understanding at home. These just show you the values of various expressions and names, etc., etc. So I am not going to explain them unnecessarily. Okay. There are other minor optimizations which can be carried out. So we search for I plus j in the hash table. How do we do it? We search for I, then we search for j, and then we search for I plus j also, right? It's not present. The reason is j plus I was obtained earlier, not I plus j. So we got j, we got I, but we can get j plus I, not I plus j. So what do we do? Whenever we have an expression of the type I plus j, and I plus j is not found in the hash table, we can always search for j plus I, provided we are permitted to do so. So this is the use of commutativity of the plus operator. Similarly, if there is a quadruple x equal to y plus 0, we don't have to leave it as it is. We can replace it with x equal to y because 0 is an identity for addition. Then y equal to j star 1 can similarly be replaced with y equal to j. You may think that these are all very trivial things. Yes, they are, but the compiler must do it because intermediate code generation process might have introduced such quadruples, okay, in abundance. So the quadruples whose LHS variables are used later can be marked as useful, and all the unmarked quadruples can be removed at the end. So this is just a way of saying that these are useless and can be removed from the program. So this is how local optimizations happen. So now let us look at another variety of optimizations called peephole optimizations. So why is it called a peephole optimization? A peephole is nothing but a small window of instructions. So when we have a window of instructions and we look at that window, it is possible to perform some simple optimizations. So these peephole optimizations actually can be within the basic block, and some of them can be across basic blocks also, but not in a on a complete control flow graph, but it is only within this particular window called as the peephole. My statement will be clear as we look at some of the simple examples that we have in the following slides. So they are usually carried out on machine code after the machine code is generated, but intermediate code can also benefit to some extent from it. So it examines a sliding window of code, which is called as peephole, and replaces it by a shorter or faster sequence if possible. So that is why it is called as a peephole optimizer. Each improvement provides opportunities for additional improvement, so repeated passes are necessary. Okay, so let's now take examples. Elimination of redundant instructions, removing unreachable code, okay, short circuiting jumps over jumps, algebraic simplifications, strength reduction, use of machine idioms. These are some of the examples. So let us look at one detailed example for each. How do we eliminate redundant loads and stores? What do we mean by a redundant load or store? So there are 4 possible scenarios. Here is a load instruction, load x comma r0. We are looking at machine code here. And here is a store instruction, store r0 comma x. Under what conditions can we remove the store instruction? If there are no modifications to either r0 or x between these two, in the code between these two, then we can remove the store instruction. So observe that there is a window of instructions called the peephole, which possibly could be 20 or 100 instructions. Okay. And in that span of instructions, if this pattern appears, then the store instructions can be removed in such a context. So similarly, there is a load x r0 and there is another load x comma r0. If there are no modifications to either x or r0 between these two instructions, then the second load instructions can be removed. Store and a load, same thing again. No modifications to x or r0, so we can remove the load because x as it is will contain the value which is in r0. Then finally, there is a store and a store. So the second store can be deleted if there are no modifications to either x or r0. So these are some examples of elimination of redundant loads and stores. Okay. How do we remove unreachable code? An unlabeled instruction immediately following an unconditional jump may be removed. Why? We have a go to L and here is an instruction. which does not have a label. How do we get to this point? We come to this point, then we jump out. So we cannot even get to the instruction which follows the go to instruction. Okay, that is the reason why this is a simple, peephole optimization. But in the first place, how are such instructions produced? They may be produced due to the debugging code which is introduced during development and never removed. And they may be due to updates to programs, say maybe for fixing bugs, whatever, without considering the whole program segment. So a little bit of laxity on the part of the programmer, because there are so many changes which are being made. Some of these may be not considered. So example here, the program is here. Okay, if print equal to 1, go to L1, following which there is a go to L2. Then we have L1 print instructions followed by L2 another sequence of instructions. Suppose print was initialized to 0 at the beginning of the program, right? Then what happens? This can be made print not equal to 1, go to L2 directly. Instead of saying print equal to 1, go to L1, and then, because now it is false, print is 0 now, right? So we are going to L2. So we can change print not equal to 1, go to L2, and then have print instructions. So that changes to, if 0 not equal to 1, then go to L2, and then you have print instructions and L2. Now, this can be evaluated and it will become go to L2, because 0 is not equal to 1, and you have followed by print instructions. Now the print instructions are unreachable, so we can remove them, right? So this is how the unreachable code gets introduced into programs, and they can be removed by a small window of instructions. Please observe here that the window is not a basic block here. Okay, so it is across the basic blocks, the many go to statements in between as well. So when we look at 100 or 200 instructions, together, we may discover such patterns, and some simple optimizations of this kind may happen. Short circuiting jumps over jumps, right? So there is a go to L1 here. That means we go to this label L1. Then we again go to L2. So we may jump to L2. Well, why should we go to L1 and then go to L2? Instead of 2 jumps, we could simply replace this by go to L2 directly, right? So now there are no jumps to L1 anymore. It is not necessary. L2 is here somewhere. So this go to L2 directly comes here, right? So now there are no jumps to L1. So the statement L1 can be removed only if it is preceded by an unconditional jump. We saw examples of this earlier. Otherwise, we could go to L1 from some other place. We are not doing a global optimization by looking at the whole program. So we cannot ignore the possibility of jumping to L1 from some other part of the program. But if L1 was preceded by an unconditional jump, then possibly we will never get to this place. Okay, so that sort of a thing may occur. Second situation, if A less than B, then go to L1, and at L1 you are going to say go to L2. Well, you can as well change it to if A less than B, go to L2, right? So thereby you are short circuiting some jumps. So third example, here is a go to L1, and at L1 you say if A less than B, go to L2. So there is only one jump to L1, and L1 is preceded by an unconditional go to, let us say. So we can replace this by if A less than B, go to L2, and introduce a go to L3 here. Okay, so this is possibly sometimes skips go to L3, but there is no guarantee. It may or may not skip L3 all the time. Okay, so these are some simple optimizations which are possible using the peephole technique. Then a few more. X square is obviously cheaper to implement as x star x instead of call to an exponentiation routine. So if we detect a call to exponentiation routine, it can be changed to x star x. X star 2 cube can be implemented as left shifts, 3 left shifts. X divided by 2 square can be implemented as 2 right shifts. Floating point division by a constant c, right? So for example, I have x by c, right? So we can write it as x star 1 by c. 1 by c is a constant which can be computed by the compiler. Okay. So then it becomes multiplication instead of division. Floating point division is expensive, so it will be replaced by a multiplication. Auto increment and auto decrement modes of addressing, wherever they are available, okay, can be utilized. So it will try to subsume increment and decrement operations if we use auto increment and auto decrement. But the processors of today, most of them don't have the auto increment and auto decrement mode. Some of the signal processing chips of even yesteryear used to have it, but now they may not be available. And finally, it is possible to detect the multiply and add pattern, which is a single instruction in many DSP chips. But it's a very fairly more difficult, it's a difficult pattern that to detect. And so most compilers do not attempt it. Any questions so far? So that kind of completes local optimizations. So we should, if you have any questions, please ask them on local, so that we can proceed with global optimizations. Okay, so here is a big list. Okay, and it is very difficult to explain how each of these optimizations can be performed. Whereas in the case of local optimizations, it was fairly straightforward. So most of these require a detailed data flow analysis information, and therefore, and have their own detailed algorithms to perform the optimization itself. So I will refrain from going into the details of how these optimizations are performed. I will give you examples of the end effect, what exactly happens because of these optimizations. There is a huge list. So instead of just reading through this list, let us take each one of them one by one. Global common subexpression elimination. We saw local common subexpression elimination. I gave you examples of, I star j, right, being computed twice or thrice in the basic block. So it is possible that something similar happens in the global scenario when you consider the whole control flow graph. Take an example. We are computing k equal to y plus z here. We are computing L equal to y plus z here. And we are computing m equal to y plus z here, right? And at this point, we are computing x equal to y plus z. Now, if the flow comes across like this, then the value of y plus z can be, which is computed here, can be reused. We don't have to compute it again here. It is exactly the same scenario here also. Y plus z can be reused. And finally, this as well, y plus z can be reused. In other words, if the expression y plus z flows and is what is known as available in quotes just before this computation or the basic block, then this y plus z need not be computed here. What do? We actually do this. We replace k equal to y plus z by u equal to y plus z and k equal to u. Similarly, u equal to y plus z and L equal to u. And finally, u equal to y plus z and m equal to u. And just use x equal to u here. So this is an example of global common subexpression elimination. We have eliminated the computation of y plus z, which was being done twice. Okay, the second computation has been eliminated. So either along this path or this path or this path, the y plus z computation happens only once. So what is the side effect of this GCSE? So take this example. We have a equal to x plus y and we have b equal to a star z, right? And following that is another piece of code, c equal to x plus y and d equal to c star z. So it is very easy to see that x plus y is a common subexpression here. So we said Eureka, we replaced it by saying u equal to x plus y, a equal to u, and finally c equal to u here. So far so good, no problem, right? Now, what really happens is that, the a equal to u and c equal to u are statements which are called as copies, because a is a copy of u produced by the first statement and c is a copy of u which is produced by the second statement. So is it possible to do what is known as copy propagation? Yes, it is possible. So what do we do here? We have u equal to x plus y. Now this b equal to a star z becomes b equal to u star z here. Okay. So we have propagated the copy. Okay. A is replaced by u. And similarly, the d equal to c star z becomes d equal to u star z. Once we do that, we discover that u star z is a common subexpression again. And we can do common subexpression elimination by the same technique. So there is a need for repeated application of the common subexpression elimination technique along with copy propagation in order to get the best benefit. Okay. Any question? Here is our large example, which gives a lot of chances for code improvement, especially GCSE and copy propagation. So I minus 1, I minus 1. Two common subexpressions here. 4 star j, 4 star j, 4 star j. Two more here. Then j plus 1, okay, j plus 1, j plus 1, j plus 1. 4 possibilities for j plus 1. So there are more in green. 4 star T6 will also become a common subexpression after copy propagation. So let us detect these common subexpressions and eliminate them. We did that. So T4 equal to 4 star j, and wherever we had j, 4 star j, we introduced T4. Okay. So far so good. And wherever we had I minus 1, we introduced T2. So far so good. Now wherever we had j plus 1, we now introduce T6. Okay. So we did this. Now it is time for a the second round, copy propagation, because there were a lot of copies, right? So now we have T10 equal to T4, T12 equal to T4, T14 equal to T6. They are all copies. So we can perform copy propagation because T17 is used here. So we can perform a copy propagation. So if we perform copy propagation, there are many more sub-expressions which become common. So for example, T7 equal to 4 star T6, T15 equal to 4 star T6, and T18 equal to 4 star T6. You have a new sub-expression called 4 star T6. So eliminate and do a copy propagation. You get a much more optimized code. So you see, even in this small bubble sort program, there were so many opportunities for common subexpression elimination and copy propagation. The code improves quite a bit. So the original code was this big, now it has become much smaller, and many variables have also been eliminated. Okay, so that is an example of GCSE. Any question?
Sir, I have a question. Can you go 4 slides back?
This one?
One more.
Yeah.
Yeah. So here in the like the right corner, the downwards.
Yeah.
So instead of introducing v, why we can't use d equal to b?
See, the algorithm uses a safe possibility, right? So whenever we have b equal to u star z is the new common subexpression, correct? So the algorithm simply takes u star z, puts it into the new variable v, okay, and then introduces a b equal to u, b equal to v. That's all. It's a very simple algorithm once the common subexpression is detected. So why? How can it be anything else? You know, if it is b equal to u, that would be incorrect, no? Because we want u star z.
No, actually, in the later part, we are using d, that is u into z. So, like, can we use d equal to b instead of introducing new variable v?
New variables are not a problem because we do a copy propagation afterwards.
Okay.
See, the point is we don't have to save. Each one of these optimizations can be done independently. Then after GCS, you run the copy propagation pass. That is how it works. So then it becomes simpler rather than trying to optimize further even there. Trying to combine optimizations is a complex process. So it is easier to separate them and then run these passes one by one so that correctness is guaranteed. That's all. There is no other reason.
Okay.
Any other question? Okay. So we did constant propagation and folding within basic blocks. Now, if you have a complete program, what does constant propagation and folding imply? Let us look at a very simple example. So here is a equal to 10 and then we have b equal to 20. So we are checking whether b is equal to 20. And if so, we want to go to the basic block B3. This is B3, by the way. And if it is not true, then we go to this basic block. Now, when the compiler looks at it, it can actually, within the basic block itself, it can find that b equal to 20, it's a constant, and this b can be replaced by 20. So b equal to 20, you know, it can see it becomes 20 equal to 20, but that's not enough. In order to bring, you know, more benefit, constant propagation and folding will have to be done as a more expensive exercise, and there is a fairly elaborate algorithm which you know is not easy to describe at this moment. So I am going to refrain from trying that exercise. But please believe me, yes, it can be done. Now b equal to 20 very easily can be evaluated at compile time as 20 equal to 20, which becomes true. So the code can be simplified as a equal to 10, b equal to 20, and this part of it, you know, we don't have to have any branch at all. It's only one way, this way and then this way. There is no branch. So a equal to 30, b equal to 35 and stop. It's a trivial program, but suffices to show the effect of propagation and folding. Okay. But this is what happens everywhere. Whenever there is a constant expression possible in the if condition go to statement of the basic block, and if that constant expression can be evaluated at that time, then only one of the branches needs to be retained. The other branch can be ignored. But if it so happens that instead of B, we had C equal to 20, C equal to 20, go to B3. And the value of C is not known to be a constant. In such a case, there is no optimization possible. You just have to retain the code as it is. Only when there is a constant expression and that can be evaluated, we can take the liberty of throwing away one part of the code. Otherwise, we cannot do it. Okay. Any question? Then the next optimization is a very important one, loop invariant code motion. What is loop invariant code? Well, to explain it with this example is very simple. Loop invariant code is the code whose computation does not get affected, okay, even if it is removed to the outside of the loop. Okay. So for example, T equal to address A is a constant computation. T3 gets the constant value of address A. So removing it to this point will not affect it at all. No problem. The same constant is assigned to T3 whether it is inside the loop or outside the loop. Similarly, T4 equal to T3 minus 4 is also a constant computation because T3 is a constant, right? So even that computation can be moved outside the loop because it will not be affected by the loop itself. This is exactly what is loop invariant code motion. To find loop the code which does not change within the loop, we start with constant computations and look at those computations which use these computations indirectly, and finally arrive at a group of statements which are all constant computations. Okay, there are also other conditions that they can use values from outside the loop, etc. But let's not get into those. So once these are done, all these computations can be moved outside the loop. Okay, so this is one example of how loop invariant code motion benefits a program. Now the number of times the loop iterates will remain the same, but these unnecessary assignments will not happen inside the loop. Then the strength reduction is a very simple, optimization, and it was very relevant in the olden days because, for example, replacing star by plus is called as strength reduction. In the olden days, multiplication was a more expensive operation compared to addition. Whereas in today's machines, both multiplication and addition for the integers take the same amount of time. Okay. So therefore, such an optimization may not be that relevant in expensive machines, but in very small processors where there is no multiplication available, only an addition is available. For example, very, very simple processors which are used in IoTs, etc., may or may not have a multiplication instruction. So in such a case, this strength reduction may become important. What is strength reduction? We have an instruction T5 equal to 4 star I. So what we really do is, we replace this T6 equal to T4 plus T5, okay, by an instruction called T6 equal to T4 plus T7, where T7 plus equal to T7 plus T4 is the instruction which has been introduced as a new instruction. There is no T5 equal to 4 star I anymore. Okay. So this is the 4 star I has been replaced. We know that I equal to 1, 2, 3, etc. It's an arithmetic progression. So I equal to 1, the value is 4, I equal to 2, the value is 8, etc. So once the compiler determines that this is such an arithmetic progression, it can easily replace the computation of star by a plus T7 equal to T7 plus T4 plus 4. So this is how, and of course there is an appropriate initialization which is necessary. The algorithm does it automatically. Okay. So this is how the strength reduction optimization eliminates the star operation inside the loop and replaces it by a plus operation with, of course, appropriate change of variables and things like that. Okay. Then the third one, which changes the landscape of a program, is known as the induction variable elimination. So, for example, in this program, we are using the variable I, which controls the loop. But then, when we did this strength reduction, right, we also introduced the new variable T7. So T7 and I actually go in lockstep, right? When we increment I, the T7 also gets incremented. So why use I? We might as well use T7. Only thing is we are using I greater than 100 here. So we must use I, T7 greater than 400 otherwise. So we can use the variable T7 in the place of I and eliminate I altogether. So the optimized program will not have I. It will work on T7. This is one reason why it is very difficult to perform debugging with optimized programs. If you turn the debugger on, most of the time the optimizations actually will be disabled. You will be debugging a unoptimized program, or only those optimizations which are very simple will be performed. Those which perform a lot of change in the which actually change the program quite a bit, like the induction variable elimination, will be turned off. Okay. Any question? Then we come to the next very important, very powerful optimization known as the partial redundancy elimination. In the case of common subexpression elimination, we had A plus B here and we had A plus B here also, and somewhere else when we had A plus B, we changed it to a temporary, right? The elimination of two computations, rather replacement of two computations by one happened, and the second computation was eliminated. In such a case, in the case of global common subexpression elimination, the expression A plus B must be totally redundant. In other words, along every path in the program which reaches that point, A plus B should have been computed. I showed you that picture already. In this particular scenario, it is not so. We are computing A plus B here. We are computing A plus B again here. So along this particular path, second A plus B is redundant. But A plus B is not computed along this path, so it is not redundant. Okay. So this is an example of a partial redundancy for A plus B. A plus B is partially redundant in this program. When there is such a partial redundancy, the only way to eliminate such a partial redundancy, of course, we do h equal to A plus B and x equal to h. This is as before, and y equal to h as before. But this h equal to A plus B will have to be introduced into this path. Okay. Otherwise, if we change this code as it is, it will be incorrect. If we introduce h equal to A plus B here, then along this path we have a computation of A plus B by the time we reach here, and we can say y equal to h. And along this path also we have h equal to a plus b computed before. So we can say y equal to h. So the correctness of the transformation is guaranteed. This is called as partial redundancy elimination. Let me give you two more examples of this. There are three more examples. So we have a plus b here, a plus b here, we have a plus b here, right? But there is nothing along this path and there is nothing along this path. So what do? If we want to eliminate the partial redundancy, we introduce h1 equal to a plus b, we introduce h1 equal to a plus b here also. And now we can say m equal to h1 at this point, x equal to h1 and z equal to h1. So this is an example of slightly more complicated partial redundancy elimination. Please observe here, a and b are being reassigned after the expression has been found redundant. This is redundancy ends here. Now n equal to a plus b is a new computation of a plus b because a and b were modified earlier. Okay. So and here y equal to a plus b takes the new value of a plus b. It is the same new value. It is not the old value. So after this, we introduce a new h2 equal to a plus b and y equal to h2. So this is a new computation of a plus b and therefore we use a different, we compute it again. All right. So that is a very important thing that the PRE must detect. PRE is a very, very complicated algorithm. So there is no hope of explaining how it works. Let me give you one more example. So we have y equal to a plus b, x equal to a plus b. Then we have y equal to a. All these purple boxes are the original code, and what is shown inside with the green boxes is the code after the PRE algorithm is run. So we had y equal to a plus b here, and we had y equal to a plus b here, and we had z equal to a plus b here. So we found that a plus b can be introduced along this path, and we could introduce along this path also. And finally, we could use the computation, and we said y equal to h here, z equal to h here, y equal to h here, right? Now there is something very important that I must point out. We still have this y equal to a plus b, and we still have this x equal to a plus b. Of course, this second a plus b is new after a equal to c, but we are not doing anything about it, right? Why? That is the question. And we have one more a plus b here. We are not doing anything about that either. See, there is a small problem with respect to this a plus b, and that is related to what is known as safety. So there is one path here in which there is no computation of a plus b, right? So introducing a new computation of a plus b here is called as an unsafe transformation. And this is the reason why we are not able to actually replace this x equal to a plus b and utilize it. In the next example, I will show you when it is possible. Suppose we had the code s equal to a plus b along this path. Now, doing this transformation is very safe. So, for example, now we can say x equal to a plus b is replaced by h equal to a plus b. We introduced a new h equal to a plus b. The rest of these are all the same. And now we introduced a new h equal to a plus b here also. Finally, this has been changed. This has been changed. This has been changed. Okay. Whatever we could not change earlier could be changed now because this particular s equal to a plus b was present along that path. And so these transformations became safe transformations. Okay. So I just wanted to show you that PRE cannot be applied without looking at what is known as the safety of the transformation. We should not introduce a computation into a path in which there was no computation before. That is called an unsafe transformation. Okay. Any question?
How does this sorry, how does this lead to like performance increase or something else? Like this only seems to have downsides.
See, the example is trivial, but in general, partial redundancy elimination actually does, as much as it's a generalization of the common subexpression elimination. So it definitely leads to improvements. So the placement of the code for h equal to a plus b, etc., is evaluated by the PRE algorithm, and it introduces it into a place where it is very beneficial. So it does improve the code. It is just that our examples are very small examples, so code improvement may not be visible. That's all.
Would it be possible for you to like provide an example where it does help?
See, all the small examples that we can show on paper will be very small. So whereas the bubble sort of an example does not have PRE, it has only total redundancy. Okay. So for example, even here, see, it is a kind of theoretical example, x equal to a plus b is computed twice here, whereas x equal to a plus b is computed only once here along this path or along this path. So there is definitely going to be the same kind of improvement as in the case of common subexpression elimination. No problem about that. It is just that the code increase may be possible, but with the appropriate placement of code, such an increase will not happen. Okay. So it's slightly general. See, with PRE, you can get rid of the GCSE algorithm. This automatically performs GCSE also. So a single application of PRE will automatically take care of both GCSE and partial redundancy. That is, so if there is no need to perform PRE, it can do GCSE. So it's not going to be harmful in that sense.
Sir, I have one small question. So, in the second path, we are introducing an extra computation that wasn't present in the program. So, does that, let's say, the program follows the second path? So, does that increase some, let's say, time? It definitely will increase some code size. But what are your thoughts if that, let's say, if second path is taken, so it will degrade performance of it?
No, because if you take this path, y equal to a plus b still is being computed.
Okay.
And here h equal to a plus b is computed, and there is a copy. The hope is copy propagation will take care of that inefficiency sometime.
Okay. So here copy propagation is also in picture. That's why
Yeah. See, each one of these will have to be followed by a copy propagation. Otherwise, it doesn't make sense.
Yes. Because I was observing the computation we are introducing and we are also increasing.
This is exactly the issue of safety.
Hmm.
If along this path, I am introducing a computation h equal to a plus b because it is safe. Whereas in the other example I showed here, there is no a plus b here.
Yes.
So introducing it becomes unsafe.
Now it makes sense. Thank you.
Whereas in this example, there is a computation of s equal to a plus b, so it is safe. That's it. So this code optimization is, especially PRE, is such a complicated placement improvement. It has to be followed by copy propagation. In fact, to the extent that you may have to apply all these optimizations again and again, and there is no way you can guarantee anything. So most compilers just do it once or twice and stop at that point. They don't keep on applying it until there is no further improvement. That's a very difficult process, very time consuming. Okay. So now the next optimization is called a dead code elimination. So what is dead code? Code that is unreachable or code that does not affect the program. So together they can be called as dead code in a very loose sense. and they can all be eliminated. So a simple example, G is a global variable outside the function, and here we have I equal to 10 and G equal to 100, but then we reassign G equal to 250, then we return from the function, and there is another statement G equal to 300, right? We are never using these two values in the function. So this is dead code, because G equal to 250 overwrites the old value and I is never used. And this G equal to 300, you cannot even touch it because control does not flow to that point. So that is unreachable code. Okay. And after optimization, obviously the code becomes very simple, G equal to 250 and return. So this is an example of what dead code elimination can do. And what is shown here is simple, but performing it is not going to be trivial. It requires a fair amount of data flow analysis, and then an algorithm to check whether there are many multiple definitions reaching a particular point, etc., etc. So even though the effect can be very easily demonstrated, the algorithm itself may not be very trivial. Slightly more difficult example of dead code elimination. We have int a equal to x plus y, right? Then we have if x greater than 0, a equal to 1. And finally, a return statement. This function actually is doing only this much, right? It is returning y. So the entire a equal to x plus y, x greater than 0, a equal to 1, they are all useless code. But detecting all this requires some data flow analysis, and to make sure that the function is not, y is not affected by any of this code, right? Then all this can be termed as useless code and it can be eliminated. Okay. So this is a dead code elimination algorithm, example. So now we go for other simple optimizations. Here is a for loop. Now it's well known that we can unroll the loop. We have S1i, S2i, S1i plus 1, S2i plus 1, S1i plus 2, S2i plus 2. So we unroll the loop. Place 3 iterations inside the same loop. Now the loop has to run with different bounds, obviously. And then there will also be some leftover iterations which have to be performed. Why do we want to unroll a loop? Every time there is a loop, it involves some checks here and then the body of the code and then back, testing and then jump. So these kind of jump statements affect the speed because they break the pipeline. Because of this, if we there is another reason. The body of the code here, the loop, may be very small, and the modern processors which can execute many instructions in one cycle may not be able to schedule a large number of instructions in a cycle because there is a paucity of instructions. If we increase the size of the body, the basic block, then there will be many instructions available for the CPU to execute. So it becomes much faster. Okay. So these are reasons why unrolling a loop may be very useful. So it is possible to unroll while and repeat loops also, but as you can see, there is an if condition in between, and so it may or may not be very beneficial to unroll such loops. Okay. In some cases it may be useful, but not in general. Here is an optimization which is performed by almost every compiler. It is function inlining. So here is a very simple function find greater. which just checks all the elements of the array and finds if ai greater than n, then return that particular I. Okay, so n is passed here, you can see. So finds an element of the array which is greater than n. Such a function which has a very simple body like this can actually replace the function call itself. So when we replace the function call, this is the code that gets inserted in the place of that assignment. So it just takes the body, rewrites it with different variables. For example, we had I and n and a. So we have new I and new a, right? And then we have assigned new a equal to y, which is nothing but the parameter here, the array. And we look at new I equal to 0, new I less than, instead of the old I here, which was a local variable, now we have introduced a new variable called new I, so that there are no name clashes possible. And then we iterate. The loop remains the same. And this if condition also remains the same, but the instead of a we use new a, and instead of I we use new I, and this is a constant, so we are using 250 as it is. Okay, and we assign x equal to new I instead of return I, which is correct, of course. Okay, and then we go to the exit if that happens. So there is a very systematic rewriting of the function body with the new variables, okay, appropriately written with different conventions, and this is function inlining. Obviously, function inlining can work only if the function is not recursive. If the function is recursive, how many times would you unroll the function, right? That's a question which cannot be answered very easily. So function inlining is the possible. Maybe I will unroll the recursion once or twice. All such experiments can be performed, okay, to see whether it gives benefit. But generally, we disable function inlining if the function is recursive. So having said that, in cases where the recursive call occurs at the end of the function, okay, it is called as tail recursion. You can see that the function sum has a call, recursive call at the end of the function. It is called tail recursion. So if there is tail recursion, then it is possible to replace tail recursive call, the entire function, by a while loop. There is no need for the tail recursive call at all. So as you can see, the function remains the same. Instead of this body with a recursive call, we have introduced a while loop, while true, if n equal to 0, x star x equal to star x plus a0, that part remains the same. And then there is a break. Okay. Else star x equal to star plus n equal to n minus 1, and then continue. So instead of the recursive call, there is a continue which goes back to the while loop. Okay. So again, this can be done algorithmically. In the case of tail recursive calls, okay, it is possible to replace them with a while loop, and that increases the efficiency of the program quite a bit instead of the recursive call. Okay. Any questions so far? Okay. So here is the last part of my lecture today. This is the algorithm called trace scheduling. So trace scheduling is generally beneficial when the different types of instruction scheduling algorithms fail. So in other words, there is a program with if then else, etc., etc. So in such a case, a large number of instruction scheduling algorithms which try to utilize multiple CPU or rather function units fail. So in such cases, a trace scheduling algorithm is beneficial. So what is a trace? A trace loosely is a frequently executed acyclic sequence of basic blocks in a control flow graph. Let me give you an example. If you take this control flow graph, this particular sequence of basic blocks is frequently executed, let us say. So we call it as a trace. That's it. So we identify a trace. It's a heuristic again. Identify the most frequently executed basic block. Extend the trace starting from this basic block forward and backward along the most frequently executed edges. How much to extend is a heuristic. And we may want to do it once or twice before we zero in on a particular value. Then apply the instruction scheduling on the trace, which can utilize multiple CPU function units. Execution time for the trace may reduce, but the execution for other paths may also increase. But overall performance will improve on the average. What do we mean? Here is a simple program with if then else condition. And now we know that this part of the program executes, very frequently. So we call it as a trace. So this is the simple assembly code which is produced by the compiler without any trace scheduling. Suppose we don't have any traces. Now trying to use the two CPU function units will give us a sequence of machine instructions in this form. So the 9 cycles are required for the main trace and 6 cycles will be required for the off trace. Even though we are not doing any trace scheduling, I'm just mentioning the main trace and the off trace so that we don't lose track of what is that we want. So we are looking at when we execute this part of the program, we require 9 cycles, and when we execute this part of the program, we require 6 cycles. That's what it really says. Okay. Now, suppose we consider the entire trace, that consists of these three as a single basic block. Then we can move instructions from here to this place, etc., etc. We can probably remove this instruction and so on and so forth. So movement of instructions along this basic block, along the 3 basic blocks will be possible. With that assumption, suppose we schedule the instructions on the 2 CPU function units, then the main trace requires 6 cycles and off trace requires 7 cycles. 9 and 6 became 6 and 7. Off trace is executed very few times, whereas the main trace is executed many times. So there is a benefit, right? And then there are also difficulties of this kind, which I am going to ignore now. So for example, speculative code motion introduces difficulties in which hardware support is also required. Okay, I will not expand on this too much, but that is something that will happen. You can't help it. Okay, so this is the last slide in my lecture today now. So if there are questions, I will take them. Otherwise, we'll stop here and meet in the afternoon. Okay, thank you. Subhajit, can we
yes,
close
sir.
the session now?
Yes, sir, we can close it. So any questions, guys? No other questions?
Sir,
Yeah.
this is Sumit from this side.
Yeah.
Sir, actually, I wanted to ask, sir, is this trace scheduling used for like some like profile guided optimizations, or like is it used in profiling or like some sort of applications there?
See, profiling actually is necessary to produce traces. Because without profiling, how do we know which traces execute, which parts of the code execute more often? So it is a profile guided optimization in that sense. Yes.
Okay. Yes, sir. Thank you, sir.
So profiling must be done. Traces must be identified. Then the trace scheduling can happen. Then possibly the program will run faster.
Yes, sir. Thank you, sir. Thanks a lot.
Sir, how do we take a call on inlining? Like, the inlining will always help in performance improvement or not? Like, and maybe which are the suitable functions to inline? Any?
See, inlining will definitely give benefit unconditionally, because when you have a function call, we are going to create a new activation record, transfer the parameters to that activation record, jump to that particular function code. Then every time you access the variables, it will imply a level of indirection because the variables are on the stack. So finally, you have to transfer the result back to the program, right? Calling program. So all this overhead will be eliminated if you have function inlining directly. So function inlining will unconditionally give you improvement. I really cannot think of, at least offline, online, I cannot think of any examples where function inlining can be harmful. It, of course, it introduces more variables, number one, and then the space required for the program will increase. That is, these are, if you say harmful effects, then they are. So if you inline every function call, then the space required for the variables and the code will increase quite a bit. That those are the two undesirable side effects.
Okay. Yeah. Thanks.